Thank you very much. I guess we all know that energy harvesting promises a more sustainable and maintenance-free alternative to traditional battery-powered devices. To transport data and coordinate activities, multiple of these devices typically operate in networks. To develop efficient protocols for these kind of networks, we need a way to reliably and fairly compare different solutions. Let's say we want to compare two networking protocols, RedNet and BlueNet. We deploy our devices and run RedNet for 1 day to evaluate its performance. Then on the following day, we run RedNet on the same devices, realizing that it performs significantly worse. Is our result really valid? Of course not. The performance of energy harvesting systems critically depends on the energy available, a factor that is extremely difficult to control in real-world distributed experiments. However, for meaningful evaluations and fair comparisons, we require controlled and repeatable conditions. Our work, Shepherd Nova, solves exactly this problem. The user can deploy the firmware on the same shared physical infrastructure, and the testbed makes sure that the energy available to the devices is consistent across different experiments. This allows us now to fairly compare RedNet and BlueNet under the same energy availability. It would also allow us to evaluate the behavior and the performance of a given application against different energy environments. So overall, we contribute the first public testbed for distributed energy harvesting systems. Besides very careful engineering, the core scientific contribution is the concept of a virtual source to emulate a wide range of relevant harvesting architectures. We also provide a very detailed performance characterization of our testbed and release all artifacts, including hardware, software, and harvesting data as open source. Let me take a minute and emphasize that I'm really just standing here on behalf of all these excellent researchers and my co-authors. This has been a team effort over the last couple of years, and I would also acknowledge our funding sources. So let's dive a little deeper into the architecture of our testbed. First of all, we have the system under test. That's, in our case, a collection of distributed energy harvesting devices, and we call each of these devices a target. And every target in our testbed is coupled with a more powerful observer platform. The observers that can control certain characteristics of the target, and it can observe its performance during the experiment in real time. The observers connect to a testbed server via a wired backbone network. The user interacts then with the server. The user provides the firmware, the configuration for an experiment. The server starts and stops an experiment and eventually delivers the experimental results to the user. Currently, we provide a target platform that features two very popular microcontrollers. First of all, this is the NRF52 from Nordic, very popular in the Census community. And the other one is the MSP430 with FRAM chip from TI, which has been instrumental for battery-free and intermittent computing research over the past decade, I would say. You can choose to use both processors in tandem, connected over an SPI interface, or just one of them and disable the other. It is very easy and convenient to attach new target platforms to our testbed simply by designing a basic adapter board. There's currently also one free target slot, so depending on the requirements and needs of the community, we can easily accommodate these at the moment in our testbed. Moving on to the observer hardware, you can see that the observer consists of 3 stackable boards. The real meat and heart is the Shepherd Nova board. It's a custom-designed board that hosts all the emulation and measurement circuitry and also connects to the 2 targets, where only one of them is present at the moment. The observer hardware runs on a BeagleBone Green, and power and Ethernet connectivity is provided by a PoE adapter. So now that we know how the hardware looks like, let's move on to the functionality of the observers. We have to remember that the key task of the observer is to control and observe the targets, multiple targets across a distributed system. So if we want to be able to correlate measurements and observations and also reproduce energy availability across both time and space, the observers have to operate in synchrony. They have to be very tightly synchronized. Our performance benchmarks show that we achieve a maximum synchronization error of roughly 300 nanoseconds, which is significantly better than existing prior testbeds. In terms of control, the main task is to provide a real supply voltage to the target in order to emulate energy availability. To do so, we essentially emulate a real energy harvesting device that is shown here on the top. So such a real energy harvesting device features a harvesting transducer that transforms, for example, solar energy into electrical energy. It also features some energy storage, a capacitor or a rechargeable battery. To make this charging process efficient, there's typically an input stage that does, for example, maximum power point tracking, and there's some output stage, for example, to provide a stable supply voltage to the load. In our testbed, we retain the physical load, so users still run their software, their firmware, on the physical target, on the actual hardware, while the rest is essentially emulated in software. So we provide a variety of models of input circuits, energy storages, and output circuits. That includes very simple ones, just a diode on the input stage, or a more complex boost converter, boost charger. We have models for rechargeable batteries and an ideal capacitor, and multiple choices on the output circuit stage as well. Users can not only choose between these models, they can also freely configure various parameters of these models. I don't have time to go into more details here, but let me emphasize that one of the key challenges here has been to select accurate models that can also run very efficiently on the observer hardware. This whole emulation loop executes with an update rate of just 10 microseconds. The physical transducer is replaced with files or data streams that are input into this emulation pipeline. We support supply voltage profiles, IV traces, IV surfaces. We have a fairly large repository of such traces, so you don't need to walk around or somehow generate your own traces. You can just choose from a variety of real-world energy harvesting traces that we already provide. Here on the left side, you see a picture of one of the co-authors. He was running around with his girlfriend in the park with solar panels and kinetic harvesters attached. And we also did experiments with an industrial washing machine, attaching 5 piezo elements at various locations of such a washing machine that was running at full load for 45 minutes. So these are just examples that you can choose from. So as I already hinted at, this emulation loop executes with a rate of 100 kilohertz. A new sample is taken from the file system, and a real supply voltage is generated to emulate energy availability. In addition to control, we can observe also the targets. So the targets are harvesting energy, and then they are doing something. They're executing a firmware, a program. And we can, for example, observe the logical state changes in the firmware with a very high rate. We are doing that by allowing the user to insert into the program code GPIO pin set and unset statements. So this is maybe some high-level code, sensing, some processing, some inference, maybe also some communication. And you as a developer can insert set GPIO pin or clear GPIO pin statements that just take a few clock cycles to execute. And we can observe and record these state changes at the output. Every such event is then combined with a timestamp from the synchronized clock. So you can not only trace logical state changes of a single device, you can do this in a distributed way to debug your code, for example. So event plus timestamp goes into the database that is eventually available to the user. All of this runs with a frequency of at least 1 megahertz. We can go up to 2.2 megahertz under certain conditions. In addition to logical state changes, we also provide power profiling, and we record any serial data that is output over the UART by the target at a rate of 100 kilohertz. So the current installation of our testbed is in a university building, as you could probably guess, spread out across cafe rooms, offices, floors. Right now, 11 nodes are active. These are the green ones here in the picture, and we already have produced 11 more nodes that will be rolled out in... Sorry, that's not working properly. All right, so one of the questions you may wonder is, what can we do with it? What is it good for? And to illustrate this, let me choose or dive into an illustrative example, battery-free neighbor discovery. We conducted an experiment on the testbed on a subset of the nodes available in the testbed. And the goal of these nodes running a specific program was to discover each other's presence. So when these devices wake up, they have no clue who's around them, how many neighbors are there, what is their identity. And to make this a little bit more challenging, we emulated battery-free devices. So these devices cannot continuously operate, they cannot continuously listen. They operate in an intermittent fashion, which means they are off most of the time. They are forced to be off and recharging their capacitors most of the time. They can only wake up for a few milliseconds to exchange messages and discover each other. And as you can see here in this picture, is very often, very likely it is that one device has energy, it powers on, sends a message, but there's no one around to actually receive the message. So let's see how this performs on our testbed. We will now focus, otherwise it would be way too crowded, on just 2 nodes in our testbed. And here you can see the harvesting power that is input to, so that's the input to these 2 nodes, the blue one and the red one. We are emulating a complete energy harvesting device with a capacitor of 100 microfarad, already quite large, I would say. And yeah, these are solar harvesting tracers, so they are real solar harvesting tracers. So we run this experiment, and we're just looking at a 4-second excerpt from this experiment. And what we see here in the lower plot is the power draw of the two devices over time. So the blue one and the red one, and all these little spikes that you can see in this plot correspond to the active phases of these battery-free devices. So they only power on for a very short time, and immediately after powering on, they send a very short message and listen for a short while. And as expected, as I hinted at before, these spikes don't happen usually at the same time. So the devices have a hard time discovering each other's presence. So what we can now see here, or do with the testbed, is that we can correlate the energy environment, the available energy on the topmost plot, with what is actually happening in terms of power and activities on the devices in the lower plot. And here, luckily, we see that during a change in the charging cycle of the blue device, because it is harvesting for a short time a little bit less energy, the charging cycle is extended, and by chance, its wake-up aligns with one of the wake-ups of the red nodes. So that constitutes a successful encounter where both devices can exchange a message and discover each other. We know this because we have already also traced the GPIO pins and all right. Second question is, how well does it perform? We conducted a series of quite detailed benchmarks, and I have to refer you to the paper for the electrical characteristics along several dimensions and metrics. We also looked at the accuracy. So how well do our emulation models actually represent real physical chips? We tested converter-based and less complex converterless architectures, and found that we achieve a mean error of about 4%. So there's a good correspondence between real and emulated behavior. And in the following, I would like to dive a little bit deeper into the precision of the testbed. So how well can we reproduce energy availability across a series of experiments, which was the main goal of our work. So let's look into the reproducibility of energy availability. We use this particular setup. We used the real harvesting trace, solar harvesting trace, quite constant because it was put in a closed light box. But a quite complex harvesting architecture with a boost charger, maximum power point tracking, and also a buck converter in the output stage. The target was executing a very simple firmware that just turning on an LED whenever the capacitor was fully charged. We conducted 10 independent runs on the same shepherd node, and we were measuring the energy that is transferred to the target by the testbed, or you can also say the energy consumed by the target over time. So these are the results, and you should have seen 10 different lines, but as you can see, they are almost perfectly aligned. So the testbed is able to consistently reproduce energy availability. So you see here over time the 1 minute experiment and the energy that is being transferred. You see extremely good alignment in the beginning and a little bit of jitter later on. Then, finally, let me say a few words about the reproducibility of activities or power profiles. Because this was an expectation that we had when we started to experiment with the testbed. We were expecting, okay, if we run experiments over and over again, shouldn't we see the same activities at the same points in time? But it turned out to be actually not the case. So we eventually, after trying the many different setups, we tried the most controlled setup that we could actually come up with. So we used a synthetic harvesting data trace. We disabled maximum power point tracking, and instead of using the real target that executes a firmware, we used a switched resistor. And the switch is closed whenever the capacitor is fully charged, just to drain the energy in a very controllable way. Again, we executed 10 one-minute runs on the same node, and we were measuring the power of the target. So here you see the results of these 10 runs, again plotted over time. And as before, with the energy availability, there's extremely good alignment in the beginning of the experiment. So there's this little zoomed in after roughly five seconds, there's this little zoomed in plot to the left, and to the right we see that all of this is kind of diverging. So we have accumulating effects of noise, limited precision, and this is something that is unavoidable in any real system where we rely on physical components. So whenever you start to maybe use the testbed, don't expect that you can reproduce activities over time. And there's a more detailed analysis of this in the paper. So to wrap up, our testbed is publicly available. You can reproduce energy availability consistently. You don't have to provide your own data. That's planned for the future. If you want, you can use our real and synthetic traces. And you can actually do mixed experiments, heterogeneous experiments with battery-powered energy harvesting and battery-free devices. And you can observe the behavior of these devices at a very high resolution in various dimensions. Unfortunately, 2 weeks ago, we were hit by Murphy's Law. Our university changed some of the access rights, and our file server went down. So after months and months of internal testing, we are right now not able to actually run experiments on the testbed, but hopefully that will be resolved in the next days. Anyway, you can go to this website and get your account already. We are eagerly waiting for feedback. We are curious to see what kind of applications you will run on the testbed. And Ingmar and some other guys from our group, they put a lot of effort into developing, getting started tutorials, documentation, and you find also all the code and so on the website. Thank you, and I'm happy to take any questions you may have.
Okay, thanks Marco for a great presentation. So now we have a couple minutes for Q&A session. So while our audience gathering their thoughts, maybe let me ask a quick question. Actually, I'm not a hardware expert, but I feel like the emulation function of the supernova seems like a single signal generator. But I know there are some specialized instruments for this function. So I wonder what's the difference between this function in supernova and those specialized instruments.
I would say the specialized instruments are very expensive, and you usually only use them for a single device, or maybe a very, very few devices on your desk. So the main difference is that you can do this now here in a very widely distributed setting, in a real testbed, where you also can do experiments on an actual mesh network. And yeah, I think this is what I would say is the main difference.
Okay.
Hey Marco, thanks for the talk. So amazing work. So it's really cool that you're able to capture and replay these energy traces, and you can do different what-if scenarios for different types of communication protocols that you might want to develop, different energy management policies on the embedded device. I'm curious if you have any plans in the future to extend your device to also capture and replay sensor data, right? Because sometimes that can be misaligned, or maybe if you're lucky, more well-aligned with power availability. So then you could capture, the dynamics of sensing as well.
Dynamics of sensing. I think this would already be possible right now, right? You can store your sensor data stream on the devices itself, using the FRAM, for example, of the MSP 430, and then relying on the synchronized clock of the observers, you can replay that. But it would be a little bit more effort on behalf of the users. So I'm taking this as an input or inspiration for us to consider this in the future. Thank you. Yeah. Sure.
Okay, then thanks again for Marco for his great presentation. So I think this concludes our session today. So still a big thank you to all the speakers for their insightful talks, and also to all the audience for your participation and also raising many good questions. So please enjoy the rest of the conference today. Thank you.